What if black holes are doors to something we cannot understand? There are places in the universe where everything we know breaks down, not metaphorically, not philosophically, but mathematically, physically, in the precise language of equations that have never failed us anywhere else. Places where the laws that govern every other corner of existence simply stop working, where space curves so severely that it closes in on itself, where time slows to a standstill and then ceases to have meaning altogether, where even light, the fastest thing in the universe, the thing that exists outside of time, the carrier of all information, cannot escape. These places are real. They have been observed, measured, photographed, and confirmed beyond any reasonable doubt. And they are called black holes. But what they actually are, what happens inside them, what they mean for the nature of space and time and information and reality itself, remains one of the deepest unsolved mysteries in all of science. Not because we lack data, but because the answers, when we reach for them, point towards something so strange, so far beyond ordinary experience, that the human mind struggles to hold them without something giving way. It begins with gravity. Of the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, gravity is by far the weakest. A small magnet can overcome the gravitational pull of the entire Earth to lift a paperclip off a table. And yet gravity is the force that shapes the largest structures in the universe, because unlike the other forces, it has infinite range and always attracts. It never repels. It never neutralizes. It simply pulls across any distance between any two objects with mass without ever stopping. And when enough mass accumulates in one place, gravity wins completely. A star like our Sun is a constant battle between two forces: the outward pressure of nuclear fusion burning at its core and the inward pull of gravity trying to collapse it. For billions of years, these forces balance. The star burns, radiates, holds its shape. But eventually the fuel runs out, the fusion stops, and when the outward pressure disappears, gravity has nothing left to fight. What happens next depends on the mass of the star. For stars massive enough, many times the mass of our Sun, the collapse is total and irreversible. The core implodes in a fraction of a second, triggering a supernova explosion so bright it can outshine an entire galaxy for weeks. And at the center of that explosion, something forms that has no surface, no edge, no physical boundary of any kind. A singularity, a point of infinite density, where all the mass of the collapsed star has been compressed into zero volume. A place where the known equations of physics produce results that are not just extreme, but infinite. And in physics, when your equations produce infinity, it is not an answer. It is a sign that the theory has reached its limit, that something is missing, that the universe is doing something your mathematics cannot yet describe. Surrounding the singularity is what we call the event horizon, not a physical surface, not a wall you could touch or see as you approached it, but a boundary in space, the point of no return, the threshold beyond which the escape velocity required to leave exceeds the speed of light. And since nothing can travel faster than light, nothing that crosses the event horizon can ever come back. Not matter, not energy, not information, not a signal of any kind. Whatever crosses that line is gone from the universe forever, or so it seemed. Because in 1974, Stephen Hawking made a discovery that turned everything upside down. Using a combination of quantum mechanics and general relativity, the two great theories of modern physics that have never been fully reconciled with each other, Hawking showed that black holes are not completely black. They emit radiation slowly, imperceptibly, over timescales almost impossible to imagine. But they leak virtual particle pairs, the same flickering quantum fluctuations we explored when we discussed the nature of emptiness, appear near the event horizon. One particle falls in, the other escapes, and the energy for this process comes from the black hole itself, which means that over an almost inconceivably long period of time, a black hole slowly loses mass. It evaporates. And this created one of the most profound puzzles in modern physics. Because if a black hole evaporates completely, what happens to all the information that fell into it? The information contained in every particle, every atom, every structure that crossed the event horizon over the lifetime of the black hole. Where does it go? Quantum mechanics says that information cannot be destroyed. It is one of the most fundamental principles of the theory. But if the black hole evaporates and the radiation it emits is completely random, carrying no information about what fell in, then that information is gone, destroyed, and that should be impossible. This is what physicists call the black hole information paradox, and it has not been resolved. Some of the greatest minds in physics, Hawking himself, Leonard Susskind, Juan Maldacena, and many others, have spent decades wrestling with it. The leading proposals suggest that information is somehow encoded in the Hawking radiation, that it escapes in a form so scrambled it is practically unreadable, but not truly destroyed. Others suggest that the answer requires a completely new theory of physics, one that unifies quantum mechanics and gravity in a way we have not yet achieved. But there is something even stranger waiting at the edges of this question, because some of the most serious attempts to resolve the information paradox have led physicists to a proposal so radical it sounds like science fiction: the holographic principle. The idea that everything that happens inside a black hole, all the information about everything that ever fell in, is encoded on the two-dimensional surface of the event horizon. That the interior of a black hole is, in some deep mathematical sense, a projection of its surface. And if that is true for black holes, some physicists have asked, could it be true for the universe itself? Could everything we experience as a three-dimensional reality be a kind of holographic projection from a two-dimensional surface at the edge of the observable universe? Could the depth, the volume, the apparent solidity of the world around you be something like an image, real in every practical sense, but not fundamental in the way it appears? These are not fringe ideas. They are being pursued by some of the most serious theoretical physicists alive today. And they bring us back once again to the question that has been running beneath every video in this series. Because if reality is a hologram, if the three-dimensional world is a projection, then what is doing the projecting and what is experiencing the projection? Because the holographic principle does not explain consciousness. It does not explain why there is something it is like to be here, inside the projection, aware of it. It does not explain the fact of experience itself. Physics keeps finding, at every extreme, at the quantum level, at the cosmic level, at the edges of black holes, that the universe is far stranger than it appears, that the solid, fixed, independent world of ordinary experience is a surface phenomenon, a layer of apparent stability resting on top of something that behaves in ways our intuitions were never designed to handle. And perhaps that is the deepest thing that black holes reveal, not just about space and time and gravity, but about the limits of what can be known from inside a system. Because a black hole is, in a certain sense, a perfect image of the ultimate question, a place where information goes in and does not come back out, where the interior cannot communicate with the exterior, where what happens beyond a certain boundary is, by definition, beyond reach. And awareness, the awareness you are using right now to follow these ideas, has its own horizon, beyond which nothing can be directly known, only approached, only wondered at from the outside. And in the next video, we will step back from the extremes and ask a question that is in some ways even more personal. What is the nature of space itself? Not outer space, not the space between galaxies, but space as such, the invisible container in which everything exists. What is it made of? Does it have a structure? And what does it mean that you are always, in every moment, inside it?